Hi everyone, this is the A-level requested topic stream, and I've got a couple of things for you and a couple of apologies as well. What we've got in this one is we've got how we work out distances in space, so that's trigonometric parallax and also the standard candle, and I've got some exam questions on that suggested by one of our viewers, and also I have got SHM and basically the graphs and all the kind of key elements that's going to allow you to solve problems for SHM. So let's jump right into that. Earlier on today I've gone through some really interesting points about how you can make sure your revision is the most effective, and talking about metacognition, so knowing how you learn best. And one of the things I like about asking you guys what your topics are that you need to study, that you want me to go through, I think that's a really good example of metacognition, of you thinking to yourself, how well do I get different areas in my syllabus, and what steps can I take to actually improve those things. And sometimes one thing is going to improve one skill, or one area is going to improve in a different way than another area. So have a little look back and watch those videos from earlier. I also talked about the black hole, image of the black hole, which is an absolutely incredible thing, and how that can lead you to just to have a little think about some of the harder questions that they can actually ask you in A-level. As I said, I do have a couple of apologies because requested and were AQA medical physics and AQA electronics, which are two like option modules, so they're like really massive units of physics, and really massive units of physics that I haven't taught before. So I do not want to dive into those and get it wrong for you, but what I am going to say to you is I'll do these in a little while, because having a little look, there isn't much about either of those two as option units out there on the YouTube. So I will have a little look over them, and I will plan something out for you guys, and I will make you a video or several videos or something about those option units that you requested. Okay, so bear with, watch this space. What we have today, we've got how we measure distance in space. That's a request from Lane. I hope you're here, Lane. And also we have SHM, which is another request. So I'm going to jump straight into the visualizer just now. So they actually mentioned this. They actually mentioned this in the examiner's feedback, the examiner's report, that students didn't have a great idea of what we call the cosmic distance ladder. Now, you don't need to know all of this, but it's a good idea to have a good understanding of like different distances in space and how we can actually measure them. And essentially you need to know these two methods, trigonometric parallax and standard candle, really, really well. And that's what this main part of this live stream is going to be all about, right? So in our solar system, which is things very close to us, we can actually measure those distances just by radar. So we can send the thing, reflect it, and receive it back in a certain time, and we know the speed of light, so we can actually work out the distances to planets and objects in our solar system in that method. For nearby stars, so this is close to us, okay, this is the one you need to know, we use trigonometric parallax. You can just say parallax if you like, but trigonometric parallax reminds you that it's an application of trigonometry, so they could ask you to use some trigonometry for it. Within our own galaxy, when it's further away from us, so not our region of our galaxy, but within our own galaxy still, we can use the standard candle, which I'll talk about in a second. And within other galaxies, we can use what's called Cepheid variable stars, which are stars towards the end of their main sequence when they start to kind of pulsate. The layers kind of expand and then contract, expand and then contract. It's a feedback cycle. As it contracts, it does more fusion, so it pushes further apart, and then contracts again. Okay, so it, you know, more fusion, pushes it further apart, cools, contracts, more fusion, pushes further apart, cools, contracts. This is a Cepheid variable star, and it tends to be towards the red giant phase. You get these kind of periodic changes in brightness, and that's what Cepheid is. So we can use that to work out the distance, but you don't need to know the detail of that, you just need to know it's a thing. So this is our cosmic distance ladder from close to far. Okay, So a standard candle, what's that? So basically we measure the peak wavelength, okay, so you get this little graph of intensity versus wavelength, and you get this peak, okay. This peak is lambda max in our formula sheet, lambda max, peak wavelength. And it turns out hotter objects have smaller peak wavelengths, okay, they have higher frequency of light given out, so smaller wavelengths. And that we can work out the temperature, therefore, by Wien's law. Wien's law simply states that the peak wavelength is inversely proportional to temperature. Okay, it's given in full in your equation sheet, and you can work out exactly what that peak wavelength or that temperature is by this equation here. Okay, remember that's not millikelvin, that's meters Kelvin. So lambda max times temperature is a constant. In other words, they are inversely proportional to each other. Then we take that temperature and we fit it to the main sequence on the HR diagram. Okay, so the temperature is related to luminosity by Stefan Boltzmann's law, which is that luminosity is proportional to T to the power of 4. Okay, or you can just think about it as using the main sequence on the HR diagram to actually tell you what the luminosity will be. Okay, the Hertzsprung-Russell diagram. So now we've got the luminosity. In other words, we know the luminosity by all our previous workings, and we can measure the intensity here on Earth, and we can apply the inverse square law, which is this one. Okay, apply the inverse square law to work out the distance d from us. So that's what a standard candle is, and that's all you're going to need to say if you have a question that says, or you recognise, explain what a standard candle is and how a standard candle works. It's just known luminosity, measured intensity, inverse square laws. There's 3 points you're going to get in there. But I think it's useful to think about knowing, how do we actually make those measurements. I'm going to talk about parallax now as well. This happens to be something that I talked about last year on live streams as well. So you can go ahead and, as you go through live streams, you'll see this exact same page. Look at that. And this is the diagram that I drew then, and I think this is the most easy to understand, and this will get you the marks for trigonometric parallax. Okay, this diagram, if you annotate as well. So this is our star that we're trying to look at here, and we're trying to work out our distance from Earth, or this is the Sun, from Earth, our solar system, if you like, to that distant star. We wait for half the year, we wait for 6 months to pass, and we take 2 measurements of the angle that we see that star against a fixed background of stars. And that angle P there is called the parallax angle. Okay, so this is if the light was parallel, and this angle is what we actually see is the angle from that parallel there. Now you need to measure it in 2 places, because really the parallax is between where you see on this side and where you see on this side. So really, if you like, the parallax angle is really this kind of difference, this change between the line of sight on one side, the line of sight on the other side. And that's going to help you when you look at the other diagram that Lane asked me to have a little look at today, because it doesn't really kind of make sense. Now, earlier on we were talking about the black hole image, and we were talking about the thing that they were measuring was 60 micro arc seconds across. Okay, I'm just going to see if I can find that bit of writing. Where did I do it? 60 micro arc seconds across, and if you work out that the resolution was 20 micro arc seconds, but the actual black hole is, if you like, only 3 pixels in that image. Okay, because we're looking at the plasma from that around that black hole, but the actual black hole is 60 micro arc seconds across. So okay, I'll just do this with 60 then. So 60 micro arc seconds. Now, one angle has 60 minutes in it and 60 seconds in each minute. So each 1 degree is 3,600 seconds. And we're talking about 60 micro arc seconds. So 60 times 10 to the 6. Sorry, times 10 to the minus 6. Divided by 3,600. Gives you 1.66 times 10 to the minus 9 degrees. Now that's its angle across. That's its angle, if you like, from one side to the other side of that black hole from Earth. Now, how do you turn that into a distance? Well, you use the relationship. I really shouldn't have. Where's the relationship? Oh yeah, sorry, it was over here. Sorry, talk amongst yourselves for a second. Oh, there it is. Sorry. Too much paper going on. The distance from Earth, if you like, is 1 over the parallax angle in arc seconds. So, what did I get? 1.66 times 10 to the minus 9. Uh, 1 over the answer. 6 times 10 to the, well, how many is that? 1, 2, 3, 4, 5, 6, 7. 6 times 10 to the 7 parsecs away. And yeah, that many parsecs is that many light years. Yeah, 200 billion light years away. 200 mega light years, if you like. Okay, that's just some maths that I wasn't thinking of doing. But anyway, hopefully this takes you through this idea of an angle being related to a distance being a parallax angle. I would strongly urge you for trigonometric parallax just to memorize that diagram and make sure you say things like fixed background of stars, parallax angle between 6 months apart or opposite sides of the Earth's orbit. Well, why is it trigonometry? Because we know one of the sides of this little triangle that it makes, which is the distance from the Sun to the Earth. Now, Lane asked me to look at this question here, which is a quality of written communication question, because you know it's got the asterisk on it. Parallax measurements are used to determine distance to nearby stars, but this is unsuitable for more distant objects. Outline how parallax measurements are used to determine distance by nearby stars. So you don't need to know that that's for they're nearby and that standard candles for more distant ones, because you're told that in the question. But you do need to be able to put this into a logical kind of 6-mark answer. So the first mark is, the first paragraph, if you like, is for talking about how parallax works. And that is essentially just go through this. You can draw this diagram for it, and you can explain that the angle is measured 6 months apart against a fixed background of stars, and then you're going to get the marks for that. And then the second paragraph is for talking about how a standard candle works, which we've gone through already. And look, exact same thing every single time. Known luminosity, measured intensity, and then the inverse square law. You can say measured brightness if you like as well. And then this is the equation that you get, the formula sheet, which I showed you earlier. That will be a kind of perfect 6-mark answer for this. Now, why do they draw it like this rather than the way in which I've just shown you? Now, it does say a suitably annotated diagram. So that's this one here, look, fixed background of distant stars. This is our nearby star, this is the fixed distant ones, and this is our Earth and our Sun. They've measured 2 angles, and it's important that you say you measured 2 angles, and they're comparing those 2 angles. Now the parallax angle is the difference between those 2 angles. So they say accept the symmetrical diagram, but this one is a bit more tricky to understand than that symmetrical one. Now think about the parallax angle really, as I said, is the difference between those 2 angles. So we look at it at one point and this is the angle we measure. We look at it at the other point and this is the angle that we measure. The parallax angle is really the change between the 2 angles. Okay, so if you draw it here, you're kind of indicating the parallax angle is just there. So in this case, the distant stars are way over here, and these 2 lines are pretty much parallel. So the parallax is how much further away from these parallel lines these things are. The difference is, the parallax angle is the difference between those 2. It's how much the object appears to have shifted in the sky between point 1 and point 2, rather than it being an individual angle. And I think that's the hard thing to get your head around. But it doesn't really matter, because you definitely get the marks for that symmetrical one. If they were to draw this star just here, then this diagram would look exactly like that diagram that we've just drawn, and the parallax angles would be here and here, rather than here and here. So there's no issue with understanding this or the symmetrical one. If you're happy with the symmetrical one, that's absolutely fine. It's a perfectly fine diagram for trigonometric parallax. Alright, I hope that helps, buddy. Okay, the next thing that somebody asked me for was SHM and SHM graphs. So I've just done that one really quickly here. Essentially, SHM falls into two kind of categories: pendulums and mass springs. And it's well worth being able to recognize them really, really quickly. Pendulums have lengths and G's, okay, and that it depends on the time period of a pendulum, depends on the thing's length, and it depends on gravitational field strength only. Nothing else affects the time period of a pendulum. Mass spring system depends on the amount of mass, and it depends on the springiness. It depends on the spring constant, so the stiffness. And if you have a more stiff thing, you have a smaller time period, so it oscillates at higher frequency. So these are the equations that govern the time period of these two simple harmonic oscillators. Now, the first graph is the potential and kinetic energy transfer graph. So all SHM falls into this category, a conversion between potential and kinetic energy. So at one point in the pendulum, it's got maximum potential. That's at this point here at the very start. You can call this minus A if you like. Okay, this is being the amplitude. This is the maximum displacement from this point here in the middle. This is 0. Okay, this is the equilibrium position. And then this point here, this furthest point here, is A. So as the pendulum swings from here, it's got gravitational potential. It's going to have maximum kinetic just here, and then it's going to have maximum potential just here. And then it's going to swing back, and it's going to have maximum kinetic and no potential there. And then maximum maximum potential here, and then so on and so forth, right? Now, I hope that makes sense. What's happening is this constant conversion between potential energy and kinetic. And the point is, the total energy in the system always adds up to the same. Okay, when the potential is at maximum, the kinetic is at 0, and when the kinetic is at maximum, the potential is at 0. Somebody's asked, why does the periods not change when the oscillations increase? Because the only factor that affects the time period is the length or the gravitational field strength. The only factor is the mass or the spring system. So there are no other factors. The time period, even as very, very short actual amplitude, then the time period stays the same. And that's just an important thing to ask why. Well, it's a difficult thing. So what happens as the amplitude decreases, because we know it's not really a closed system, we are going to have some waste energies. There's going to be some friction up here in the pivot. There's going to be some air resistance. As the amplitude decreases, energy does leave the system, so ET comes lower and lower and lower down, but the graph shape stays the same. It's just a smaller maximum energy. Does that make sense, Luca? I hope so. Okay, do let me know. All right, so then this comes from this equation here is the most important equation on the actual sheet. This is like Hooke's law, but with a minus. This comes from this graph, right? Because at this point here, minus A, there is a maximum restoring force towards the equilibrium position. That's positive. Now at this point A, which is the maximum, the largest delta X, if you like, the largest change from that equilibrium position, there is a restoring force towards the equilibrium position. So it's a very important definition, right? Now this has three kind of aspects to it. There is a restoring force which is towards the equilibrium position. Okay, it's opposite from the displacement from that equilibrium position, and there is some constant which governs how that governs the size of that force, and that constant is from L over G or M over K. And so this equation here is the definition of SHM. If it is simple harmonic motion, the force is proportional to the distance from the equilibrium position and it's towards the equilibrium position. You can also talk about that in terms of acceleration. Okay, so really you don't need to think about the mass at all. You can think about acceleration is proportional and towards the equilibrium position. Okay, that makes sense. Right, now, and from that, and you know, if you can derive with trig, then by all means you can do this. But from that you get these graphs. So the first graph is the displacement, and let's imagine I'm going to move my pendulum to one side. I'm going to start the oscillation from this side. I'm going to start from this side because I'm going to just start from positive side just because that's kind of convention. So I'm going to pull my pendulum to this side, the positive side, and it's going to therefore have a maximum displacement from the equilibrium position. So it's going to start accelerating towards that, yeah, because the force is proportional and towards the equilibrium position. It's going to start accelerating. That means the graph's going to get steeper and steeper and steeper and steeper and steeper. Yeah. Now it's going to go past the equilibrium position at maximum kinetic energy, and so it's going to be the fastest it ever is as it goes past the equilibrium position, past zero. And then as it gets away, the force is going to be towards the equilibrium position, so it's going to slow down, slow down, slow down, slow down, slow down, until it's going to reach zero speed at the opposite side minus the amplitude. Then it's going to start increasing and accelerating towards that equilibrium position. It's going to be the fastest it's going as it goes again past that zero there. And then it's going to start accelerating towards it again and end up with zero speed at the, or back at the other side now, aren't we? So this was done one full swing from starting the furthest away to maximum speed to being the furthest away on the negative side to maximum speed to being the furthest away on the positive side again. So that process will continue to go. Now it might have a decreasing amplitude as it goes as well, but I haven't drawn that, it doesn't really matter too much. Now hopefully you recognise that shape of graph, and if you do A-level maths, I'm absolutely sure that you will. That is a cosine graph. Now in the equation sheet, they are kind enough to give you these three equations, so hence they give you these three graphs. Now I strongly recommend that you actually just sketch on the shape of these three graphs onto your equation sheet. It's going to help you to sketch them out if ever you need to know. Now also when you're drawing these graphs, draw them one directly above the other so you can think about certain points on those. So carrying on then, let's think about what that means in terms of our motion graphs. This is a displacement versus time graph. This one, which we want to sketch now, is a velocity versus time graph. Well, how are they related? Velocity is just a change in place displacement over time. So, oh, hang on, that looks very like something, doesn't it? That is just the gradient, that is just the differential. So what is the gradient at this very start? Well, it's zero, isn't it? We've pulled it away, pulled it to its maximum position, its amplitude, its maximum displacement, and it's got no speed at that point. And then it's going to start to accelerate towards the equilibrium position, so it's going to gain a negative velocity. Oh, and look, yes, that makes sense, doesn't it? Because its velocity is increasing, the gradient of the graph is getting larger but more negative, of course, as it approaches the equilibrium position. And then at the equilibrium position, it's zero displacement, it's maximum speed, it's maximum kinetic energy, zero displacement. And then it's going to increase in speed again, and it's going to go, sorry, I apologize. It's going to accelerate towards the equilibrium position, and it's going to have no speed at all when I've just messed up, haven't I? So it started from the amplitude, maximum but negative, so minimum if you like, speed at the equilibrium position. Then as it goes away and it's still accelerating towards it, okay, it's going to reach zero position at minus the amplitude, and then up to a maximum speed as it goes through the equilibrium position again, and then accelerate towards it but moving further away from it all the time, and reaching the amplitude again with zero velocity, and then accelerate towards it, maximum velocity, and so on. Now here, listen really to this main point here. We've just used the slope of this graph to make this graph. Okay, and this is, well, you'll hopefully recognize that that's a negative sine graph. So minus amplitude omega, which is the angular velocity of the thing, sine omega t. So these equations are equations for the position at any point on that graph. So if you just take time and you input that into that graph, you'll get any position on that graph. Now moving on, well, how is a velocity time graph related to an acceleration time graph? Oh yeah, well, acceleration is just the rate of change of velocity, isn't it? It's dv by dt. So how's its velocity at the very start? Well, it's a maximum gradient but negative at the start. Okay, so there we go. So it starts down there. Max negative acceleration. And then as it goes through the equilibrium position, it's got no acceleration at all, because acceleration is proportional to the distance from the equilibrium position, remember, but also towards it. And then it's going to have maximum acceleration as it is now the furthest away from the equilibrium position. And then it's no acceleration when it is on the equilibrium position. It's going at its highest speed. And then it's going to be accelerating towards the thing again. And now negative because it is the furthest away from it, and positive, and so on. Now, as I said, there's lots of ways to do this. You can do what I've just done and try to kind of talk my way through it and plot those points. Or you can remember that this is the gradient of this is the gradient of this, by using our ideas about what the slopes of graphs are. You can, if you're completely fluent with these things, you can make sure you know what the differential of cos is and the differential of minus sine is. Okay, this is now a negative cos graph. Or you can just remember these things as being related to those equations for simple harmonic motion that they give you in the specification, in the kind of equation sheet. That's really it. That's all I kind of have planned for you all today. I really hope that helped. I'll just go into this kind of view to see if there is anything that anyone's kind of wondering in the chat. You're very, very welcome to ask. I don't think there's anything. Somebody earlier on asked for if I could explain dark matter. Nobody can explain dark matter just yet, so I don't know if that was a silly question or not. Like, can you explain why we know it exists, I guess? Like, might be your question. Well, we know it exists because the universe doesn't appear to be slowing down its expansion. It appears to be accelerating. And it's dark because we can't see it. So it doesn't interact with light, it appears anyway. So we have really no way of detecting it yet, but we're working on it. And again, it's not me, it could be you guys, couldn't it? It could be you guys. All right, thanks very much. It's been a pleasure spending time with you this Easter. Crack on with your revision. There's loads of suggested videos in the description, okay? There's loads of things that you can do. Please do let me know if there's things that I can help you with, and I will try my very best to get involved and help you out with that. Okay, all the best.